Okay, so this is going to be a short video, hopefully, over the first part of chapter 13. All right, so 13 is talking all about solutions. And solutions are homogeneous mixtures, and they have two parts. And when we say homogeneous, that means they look the same throughout. So the two parts are the solute, which is the substance that's being dissolved, and then the solvent, which is what it's dissolving into. So for the next several slides, let's think about water and salt, where salt is going to be dissolved into water. So salt would be the solute and water would be the solvent. Now, how well these solute and solvent mix to form a solution is based on the natural tendency for things to mix, as well as the intermolecular forces. So if we think about a perfume bottle and I just leave it out and I leave the lid off and I let it naturally mix with the air, so that would be two gases that are mixing together. If I just leave it alone, this process is spontaneous. And as it mixes, it gets evenly distributed. And that means that it's more random. And this randomness is what we call entropy. Now, when we have a solution, in forming a solution, having the randomness increase or the entropy increase is favorable, which means it's going to happen on its own. Now, when we look at the second piece, which was the intermolecular forces, we talked about three different intermolecular forces last semester. We talked about hydrogen bonding, dipole-dipole forces, and London dispersion forces. In addition, we also talked about a fourth one, which was an interparticle force, and this was an ion dipole between something that was ionic and something that is polar. So when a solution is formed, there are three steps that have to happen. First is I have to break apart the solute. So in the case of salt, salt forms a crystalline solid, and I have to have those pieces of individual little salt particles separating from each other. And that's going to require energy, meaning it's going to be endothermic. I also have to break apart the solvent-solvent interactions, meaning in the case of salt dissolving in water, water is the solvent, so I have to break those individual water molecules apart. And remember, those are held together by dipole-dipole forces and hydrogen bonding. And again, that's going to require energy, so that step is endothermic. Now, the third step is I'm going to now have to form new interactions between the salt and the water, or in other words, the solute and the solvent. And this typically releases energy, meaning exothermic. Now, whether or not this whole process is exothermic or endothermic depends on the amounts of those three steps. So when we talk about the heat of a solution, that is the energy that's involved in making a whole solution. And it is the first two steps, which are going to be endo, and the third step, which is exo. And if I add all those together, depending on those amounts, it could be exothermic or endothermic. Meaning when you mix the solution, it might get very, very warm, or when you mix two things together, it might get cold. Okay, and it depends on the amounts of those steps. Now, obviously, in the case of water, since it had very strong intermolecular forces, we know this step 2 is going to be fairly large. And in ionic compounds, first step is going to be very large. All right, so when we talk about an ionic solid in water, like the case of salt and water that we've been talking about, any time that water is the solvent, we say that this is an aqueous solution. So those ions would be labeled aqueous. And this whole process of dissolving is called hydration. Now, it's only hydration when we talk about water being the solvent. All right, so we talked about those energies 2 slides ago. So we have the overcoming the intermolecular forces of the solute, overcoming the forces in the solvent, and then mixing them together. That would be our step 3. So if this process is exothermic, then it's spontaneous and it usually happens on its own. However, if an endothermic reaction is going to occur, that means that the third step must be close to those first two combined, meaning the exo part and the endo part should be close to each other. Okay? And entropy, which is that disorder, that randomness, plays a role in this when it is not favorable, meaning endothermic solutions aren't usually spontaneous, but because of that randomness or the entropy increasing makes it favorable, a lot of times those will occur. All right, so over the next few slides, we're going to talk about different ways of thinking about concentration. So when we talk about solubility, we assign a number that says this is how much of the solute will dissolve in a certain amount of solvent at a particular temperature. So for example, we could look up table salt and it would tell us, so many grams of salt can be dissolved in 100 grams of water at a certain temperature. Because if we change the temperature, that's going to change how much would dissolve. Now, if it's a saturated solution, that means it contains the maximum amount of solute that can be dissolved at that temperature. In other words, it is at the solubility level. Now, if it's unsaturated, that means it hasn't yet reached that solubility level that more could be dissolved. Okay, so when we look at that solubility, and let's say our solubility happens to be 5 grams in 100 grams of water. That means if I tried to dissolve 4 grams, then the solution would be unsaturated because I haven't yet reached the 5 grams. Or if I had 5 grams and that was the solubility, then that would be a saturated solution. Now, if I try to add more than that, so if I try to add more salt than would hold, then the rest of the salt just sits at the bottom of my cup. So if I have a cup and I'm putting salt in there until it dissolves and stirring it, it's going to keep dissolving more and more, meaning it's unsaturated. Eventually I'm going to get to the point that no more would dissolve, and if I continue to add some, it's going to settle out at the bottom of the beaker because it won't hold anymore. Now, there are solutions that are called supersaturated solutions. And in this case, they hold more than what can actually be dissolved, meaning they will hold more than their solubility. Now, this is uncommon and rare because we're forcing it to do something that makes no sense. We're saying you could dissolve 6 grams when you can only hold 5. So these are uncommon, and because of that, they are also very unstable, and it's very easy to get them to crystallize. And this is a process called seeding. So I have a supersaturated solution, and it looks to me like everything is dissolved. I add one single crystal, and all of a sudden you can see crystallization occurs throughout this whole solution. It's like you added that one seed crystal, and all of a sudden the whole solution was like, oh shoot, yes, I'm way past my solubility, and it all just starts to crystallize. All right, now when we talk about whether or not a solution will form, we talk about those intermolecular forces, and that phrase that we use is likes dissolve likes. So things that have similar intermolecular forces will be soluble. So water that has hydrogen bonding and dipole-dipole would dissolve with acetone, which has dipole-dipole forces because they are alike. Hexane has London forces and heptane has London forces, so those would be soluble in one another. However, water, which has hydrogen bonding and dipole-dipole, and hexane, which only has London, don't mix because their intermolecular forces aren't similar. And the lab that we did at the end of first semester dealt with this about solubility, where you were mixing several things together in a test tube, and then you had to talk about the intermolecular forces for each one, and then predict whether or not you thought they would be soluble, and then record the results of whether they were actually soluble. Along with this, if we talk about an example of this in the body, most of us, well, I shouldn't say most of us, some of us take over the counter like a multivitamin. And when we talk about the vitamins that we need, they could either be polar, meaning they dissolve in water, so those would be called water-soluble vitamins, or they would be nonpolar, meaning they don't dissolve in water, but instead would dissolve in fat. So if I take an extra amount of vitamin C, that extra amount of vitamin C dissolves in water because vitamin C is a polar vitamin. And if I have too much or an excess of what I need, I will simply excrete what I don't need. However, if I take more of a fat-soluble vitamin, meaning one that is nonpolar, then it does not dissolve in water, it doesn't get excreted, it gets stored in the fat cells in my body. And that means over time, if I keep taking too much of it, it's going to build up to a toxic level, and I could develop a condition called hypervitaminosis. Okay, and the vitamins that are fat soluble are vitamins A, D, E, and K. Things like vitamin C are water soluble. So I just am getting over a cold, and so to kind of help boost my immune system, I took some extra vitamin C. If you buy like Airborne has extra vitamin C in it. You can't take too much, meaning it's going to be excreted whatever you take too much of. But if it's a fat soluble vitamin, that's where you need to be careful. Okay, we talked about things being soluble and insoluble. If they are insoluble, we can, and soluble, if something is soluble, it could also be miscible. And if it's miscible means it will dissolve at any concentration. So alcohol in water is miscible. I could put a little bit or I could put a lot in and it always dissolves. It never reaches a point where it's at its solubility. So I don't have like an unsaturated or a saturated, it just mixes at any concentration. There is no limit. If it's immiscible, that means they don't mix. Okay? And hexane, which is nonpolar, and water, which is polar, would be immiscible because they would not mix. Now, there are some factors which will affect the solubility. And one of those is pressure. Pressure does not affect solids in liquids, so our salt dissolved in water would not have any difference if pressure was increased or decreased. When we talk about pressure changes, this is for gases, so a gas dissolved in a liquid. And this is dictated by what's called Henry's Law. And Henry's Law says that the more pressure that I have for my gas, the partial pressure of that gas, then that means a higher solubility. And if you look at this graph that's on the right side here, you can see that all of these gases, as the pressure increases, so does the solubility. And the equation is that the solubility of a gas is equal to K, the Henry's Law constant, times the partial pressure of that gas. Now, temperature also affects our solutions. For a solid in a liquid, that would be all of the lines that you see going up over here on this graph. As the temperature increases, the solubility increases. So if I were to heat up the water that I'm dissolving the salt into, if I heat it up, more is going to dissolve. Now, if I think about NaCl for the salt, notice its solubility doesn't increase too much when I increase the temperature. But if I were to look at something like potassium iodide, which would be like iodized salt, we can see that it does increase a little bit as I increase the temperature. Now the bottom graphs show the opposite trend, and these are gases. So for gases dissolved in a liquid, actually increase the temperature lowers the solubility. And that is good because when we think about where fish tend to live, this is in the colder part of the water, and the colder part of the water is going to be more gas or more oxygen dissolved in it. This also plays a role in how we serve our beverages. So things that are solids dissolved in liquids like tea and hot cocoa and coffee, we tend to serve warm, and that's because as the temperature is higher, more of it would dissolve. So we would have more coffee flavor, more cocoa flavor, more tea flavor. However, when we serve our soda drinks or our pops, we tend to serve them cold. And that's because we want the carbon dioxide to stay in there. Nobody wants to drink a flat pop. So if we lower the temperature, that's going to increase the solubility. So as it's colder, more of the carbon dioxide is going to stay in there. All right, so here's an example problem. It says calculate the concentration of carbon dioxide in a soft drink, and it has a partial pressure of 4 atmospheres, and the Henry's law constant is 3.4 times 10 to the minus 6. So the solubility is equal to the Henry's law constant times the partial pressure. So I take the Henry's law constant that they gave me times the partial pressure, and I get 0.14 molar, and that would be my solubility, and that's in molarity. Now, we are going to be looking at a way to measure concentrations. We can be very vague and say that they are just dilute or concentrated. The problem with this is dilute means I don't have much, concentrated means I have a lot. But that's very subjective because what one person thinks is very concentrated, another person might think is fairly dilute. Kind of like when we think about spiciness. What one person thinks is really spicy, another one might think isn't spicy at all. So we're going to try to assign numbers to these. That's where we want quantitative measurements. And so we're going to look at ways to measure concentration like mass percent, percent by parts per million, parts per billion, mole fraction, molarity, and molality. And we have seen mole fraction already. That was the X that we used last semester. We've already looked at molarity too, the capital M. We used that last semester. All right, so an example on mass percent. Mass percent means per 100. So I would take the part that I have of my solute divided by the part of the total. This would be the entire solution, so solute and solvent. So part on the top, total on the bottom, and then I take it times 100 to make it a percent. And here is, we're going to go to the example. So if I have 13.5 grams of glucose in 100 or 0.1 kilograms of water, and we want to know the percent mass, I'm going to take the glucose over the total. But these units are going to have to agree. Right now I have one in grams and one in kilograms. So 0.1 kilograms would be 100 grams. So I'm going to take the part that is the glucose, 13.5, over the total, 100 plus 13.5, and take it times 100 to get my percent. And when you do this on your calculator, don't do 100 and then a percent button, just do times 100. And then you label your answer in percent. And 3 sig figs gets me 3 sig figs. All right. Next one is on parts per million. And it won't let me go back. I don't think. It won't let me go back to a different slide. So when we talk about parts per million, this is the part over the total, but instead of multiplying by 100, I multiply by a million, which is 10 to the 6th. So in this problem, I have 2.5 gram sample of water. It has 5.4 micrograms of zinc, and they want to know the concentration of zinc in parts per million. And again, these units, those aren't agreeing. So if I take the zinc part and I convert it to grams, I get 5.4 times 10 to the negative 6th. Then I'm going to divide that by the total, which would be 2.5 plus 5.4 times 10 to the minus 6th. And you can see I left that off the bottom because 2.5 plus this really small number is just going to be 2.5. And then I multiply by 1,000,000, which is 10 to the 6th, and I get 2.2, and the label is ppm for parts per million. The only difference between parts per billion is I would multiply by 10 to the 9th, which is parts per billion, because 10 to the 9th was a billion. And 2 sig figs, 2 sig figs, 2 sig figs. All right, molality. And I should have put this after the next slide. Molarity, percent mass, parts per million, and parts per billion all have the part over the total. Molality is different. Molality has the moles of the solute divided by just kilograms of solvent. So moles of solute divided by kilograms of solvent. Now in this case, I have 4.35 grams of glucose and 25 milliliters of water. So this is my glucose, my part, and I need moles out of that. So I'm going to take the grams divided by the molar mass, and I get my moles. Now I have to turn 25 milliliters of water into kilograms, so I'm going to need the density. So if I take 25 times the density of water, I'm going to get 24.9 grams and then convert that to kilograms. And then molality is moles of the solute, the glucose, divided by the kilograms of water. And I have 3 sig figs, so 0.968. I would label this little m for molality and pronounce it 0.968 molal. If it's molarity, it's a capital M, and I pronounce it molar. All right, so mole fraction we've already used. That's that X. And in that case, it is moles of the part over the total moles. Again, part over total, like all of them, except for molality. And here are those equations for molarity, which we've already used, and then molality, which we just used in the last example. And there is an error on here. I'm going to have to fix this. Molarity is moles over liters. Molality, so instead of saying molarity, this should say molality. I'll have to go back and fix that. So molality is moles of the solute over kilograms of solvent. It's the only one that is different on the bottom. All right, and that's where we are going to stop for part 1.